In this section, I want to take a look at the differences between kinetic and potential energy, the work kinetic energy theorem, and then talk about different types of potential energy. Because there's more than just one type of potential energy. We talked about potential energy as a function of height in that little example just now. But there's also potential energy. Remember I talked about the example in the last section with the spring-wound car where you pull back and it winds a spring, and then the spring is what propels it forward? That's what's called potential energy in a spring, or stored potential energy. There's also potential energy in the bonds of atoms. So you learn in chemistry, when bonds are broken, it releases energy. Well, because it has some sort of potential energy within those bonds. If you deform the shape of a molecule, you need energy to change the orientation of those bonds. So there's potential energy in many different ways, not just mechanical potential energy as a result of height, but other types as well. I'll talk about those, but we will specifically look at height and spring energy, those two things. Okay, amazing thing, by the way. When I get to them, I'll go into a lot of detail. But anything in the world can be modeled with springs. Like anything, literally. Like this desk could be modeled by a set of springs with a certain vibration frequency and a certain stiffness. It's really kind of cool stuff, actually. That was one of the big things that I studied in engineering. So, kinetic energy, all right, as we said a moment ago, is the energy associated with an object's motion. The object's motion. And the formula for kinetic energy is 1/2 mv squared. Okay, 1/2 mv squared. You know what m is? M is mass, v is velocity. Okay, you've seen this before. This is not something that I need to go over those variables with you for. Now, the question though comes about, how does this turn out to be joules? How does this turn out to be joules? What are the units of mass?
kg.
Kg. What are the units of velocity? And that is squared now because the whole quantity is squared, right? Take a look up here. Velocity is squared, so the units are also squared. So as a result, I get kg m squared over s squared. But in the last section, in section 5.1, I told you that a joule was defined as a Newton times a meter. Right? Remember that was the last section? A Newton times a meter. But what's a Newton? It is. And then that's times m. So as a result, you get the same thing. Very good memory. So a Newton is really this. kgm over s squared. Well, now you have m times m, giving you that m squared right down there. So 1/2 mv squared is actually joules. It's not just made up. It actually is. It's the same thing as a Newton times a meter. All right, let's look at our first example of this. 12-kilogram bowling ball moves at 3 meters per second. How fast must a 4.5-gram bouncy ball travel for it to have the same amount of kinetic energy as the bowling ball? So you take a bowling ball, you roll it with a certain velocity. You take one of the, the bouncy balls, those like super balls we call them. They bounce and they go like crazy high. With only 3 grams of mass. With only 3 grams of mass. So how can I figure this one out? What could I do? I want to know what the velocity should be of the bouncy ball so that it has the same kinetic energy as the bowling ball. Victoria, give me a starting point.
Isolate the variable for. Can you do that?
Sure.
Okay.
So what's the formula to start?
K equals 1/2 mv squared.
All right.
So then that's square root give square maybe first. Or just multiply by 2.
I'd multiply by 2 and divide by m.
Alright. And then times.
And then take the square root, like you said?
Yeah.
Perfect. I was trying to show steps. So Victoria said multiply by 2, divide by m, and then take the square root. So twice the kinetic energy over mass is what velocity is. But the question is, what is this kinetic energy? What is this referring to? So I think the way Victoria was approaching this was, I think that she was calling this the second mass, meaning the bouncy ball, and the velocity of the bouncy ball. Is that what you were trying to solve for? Because that's what the problem says, right? How fast must the bouncy ball travel? So these are all 2's there, but KE is the kinetic energy. We want it to have the same kinetic energy as the bowling ball. But what's the kinetic energy of the bowling ball? How do I find the kinetic energy of the bowling ball? KE1, I'm going to call that, for the bowling ball.
1/2 times 12 times 3 squared.
Very good. 1/2 times mass 1 times the velocity squared. So what's the kinetic energy of the bowling ball? Let's come up with a number. 1/2 times 12 times 3 squared. 1/2 of 12 is 6. 3 squared is 9. 9 times 6 is 54. Again, this kind of stuff, please don't waste your time in a calculator. You can do it faster in your head. So 54 joules is the amount of energy that the bowling ball has. Well, if we want them to have the same kinetic energy, I could set that equal, right? I could take this 54 and make it the energy that the bouncy ball has. So now my equation becomes a lot simpler. I could say 2 times 54 all over the mass of the bouncy ball. What's 3 grams though? Remember, everything has to be in kilograms. We always use kilograms. What's grams? And 3 grams into kilograms. 3 grams into kilograms. Josh, what do you got? Not 0.3. All the way around. 0.003. You got to divide by 1,000. So the mass is 0.003 kilograms. Okay, the mass of the bouncy ball is 0.003. Oh, why did I get 3? I'm sorry, it's 4.5, isn't it? I'm crazy, sorry. Hold on, change that. It was 4.5 grams, so this should be 0.0045. I had the 3 in my mind from the velocity of the other one. That's the mass right there. So take your answer, 2 times 54 all over 0.0045, and then take the square root of that answer.
I got
150.
4.9.
Yep.
Yeah.
Very good. Now, it's not joules because we're looking for velocity, so it's meters per second.
No, I was just typing numbers and I didn't realize.
Now, there's another way you could start this problem, and it's the same answer you'd get. Okay, there's another approach to it. And the approach I would have taken, it's the same thing. Again, it's the same answer. But the other approach I would consider is this. Start the problem by saying, we want the energy to be the same, right? It said, find out the velocity so that they have the same kinetic energy. So you could have started the problem by doing this. And then this. Where 1 is the bowling ball and 2 is the bouncy ball. All right, you could have done this. Then, if you wanted to solve for the bouncy ball, you're trying to solve for V2. The 1/2s cancel. And then you could divide by M2 and take the square root. This is another way to solve this problem that, it might be useful to do it this way if you'd like in the future. Okay, go ahead and try the numbers in there, please. Check your numbers in this and see what you get. So take mass 1, which is 12 kilograms. Multiply it by 3 squared. Then divide that by M2, which is 0.0045. And you will get the same exact answer. Okay, I'm leaving it to you to check, obviously. I'm not going to write the answer twice. It's the same answer you got up here. But again, an alternate way to solve this kind of a problem. All right? Let's go to our second slide. Potential energy, I want to talk about what's called the work kinetic energy theorem. And I'm going to quickly spend maybe just like a minute deriving this, showing where it comes from. You don't need to do this on a test. You don't have to derive it and show where the formula actually comes about. All you have to do is be able to apply the theorem. Okay, the work kinetic energy theorem. So, if we think about it, start with your definition of work in one dimension. What's work? What's the formula for work? Work equals?
And what have
FD cosine theta, right? FD cosine theta. Now, if we're looking at an object that's moving, guys, focus. If we're looking at an object that's moving in the same direction of the force applied, okay, that's the only time this kinetic energy theorem actually works. All right, so as a result, we're going to have a value of theta to just be 1, really. So this simplifies to become work equals F times D. Now, what does Newton's law tell us F is equal to? F equals? MA. So right now I'm mad. All right. Then, I think about this, and I remember my associative law of multiplication tells me I can do this. Right? I can do that. I can group differently if they're all multipliers. It's not a plus sign. I'm not distributing, none of that stuff. But I can group that easily. Okay? Now, AD, what is AD is the question. Well, that's acceleration times the displacement or distance. So if I go back to my formulas and go back to kinematics, and I'll write it in red up here, this formula, see how there's AD there? I put a D instead of X. Okay, we're moving only in one direction, so I can put this D here. D and X are the same thing if I'm only moving in one direction in this problem. So if I were to solve this for AD, solve this for the quantity AD. So subtract VI squared and then divide by the 2. I'm going to solve this one separately, then we'll put them together. So subtract VI squared, that gives you 2AD, but then divide by 2. So AD is really VF squared minus VI squared over 2. So I can take this quantity right here that we've solved for AD and plug it in for that quantity right there. And as a result, I get the following. By substitution principle, right? Like we did with our linking variable Fn. I'm just showing the derivation again. It's not something you have to repeat. I just want you to see how to do it. So I get this result at the end. And this looks oddly familiar to me. Might not look familiar to you right at the start, but it looks pretty familiar to me. Here's how you can make it more familiar to yourself. Distribute the m to both of the numerators. And then separate this into two fractions that are both over 2. So distribute the m. It'll make it look a lot more familiar to you. Distributing the m, we get mvf squared minus mvi squared all over 2. Then break it into two fractions. And when you divide by 2, what does that really mean? It means multiply by 1/2. Very good. So as a result, this formula turns out to be 1/2 m vf squared minus 1/2 m vi squared. Well, these right here are just kinetic energy. 1/2 mv squared, 1/2 mv squared. So really, the final answer, or the final result we get here, come on, page move. The final result, we think about the work kinetic energy theorem is this. This is KE final, and this is really KE initial. So our result that we want to write down and like circle is this last line right here. The work done on an object is equal to the difference in the kinetic energies of that object, or the change, the delta KE. That's really what you want to write down. I just wanted to show you the derivation because some of you, I think, keep up with it and can understand what I'm doing there, and I want you to do that. Do me a favor, look at your formula sheet real quick. Open your formula sheet on your Google Doc. Open your formula sheet, please, and go ahead and take a look at the word kinetic energy theorem. How did I write it on there? Open your formula sheet, please. How did I write the word kinetic energy theorem? It's on the left side. It's right after, it's probably right after the kinetic energy definition.
I have it right.
Okay, there it is. It's the third thing down in the third section there. See, it says W equals delta KE. On your formula sheet, I write it like this, just so you're aware of this. On the formula sheet, I write it like this. But delta, as Ed told us a little while ago, really means final minus initial. Okay, so if you see it written this way on your formula sheet, you should know that it really means this. And that this really means this. Okay, but the formula you're given is W equals delta KE. You need to write this as a result and then substitute in these two quantities above. Let's look at an example that involves the work kinetic energy theorem. Now be honest before you look at the next example, raise your hand if this is true about you. How many people love the feeling of putting new socks on? Right, isn't that an awesome feeling? Okay. Now, follow up. How many people even more love sliding across the floor with like new socks? Alright? So the next example is all about that. So you should be real excited.
The point of no return.
Alright, Jake, read it for us, nice and loud.
I don't look boring, just slide around when you just put on a new pair of socks, your mat is 2 kilograms, and you start to slide with a speed of 1.5 meters per second. How far will you move the coefficient of kinetic friction between your top and the floor is 0.25?
So in this problem, these numbers, by the way, are actual numbers that make sense. Like 50 kilograms, that's like 120 pounds, 140 pounds. Initial speed of 1.5 meters per second is reasonable. A meter every second would be this, right? That's a meter every second. So I'm going a little faster than that, and then I start sliding. 0.1 or 0.25 between socks and a wooden floor is a relatively good value, right? That's our UK. Very good. So let's list what we know. We know mass is 50 kgs. Initial speed, guys, you got it? Listen. VI, okay, is 1.5 meters per second. Keep going, keep going. What's your final speed in this problem? Why? Because you want to find when you stop. Very good. When you stop. Okay, how far are you moved before you stop? What are you trying to figure out? You're trying to figure out the distance traveled in this problem or the displacement, either one, because it's the same direction. Okay, D equals X equals question mark. Which one? You know, it doesn't matter which one of those we look for, really. All right, and remember that mu K is really 0.25. So let's use the work kinetic energy theorem. All right, let's use the work kinetic energy theorem. The work kinetic energy theorem tells me W equals KE initial, final minus KE initial. What is the formula for work? What is the formula for work? For work. All right. And kinetic energy, somebody else. Kinetic energy, what's the formula? I know them. I ask you so you hear them out loud. That's why I'm doing this. Good. Half m, this is Vf squared, minus half m Vi squared. Now, the final velocity is what again? 0. So does that part matter?
No.
All right, so on the next line, let's write this without this piece right here. That all goes to 0, because 0 times anything is 0. So we've got F times D times the cosine of theta equals negative 1/2 m Vi squared. What am I looking for, folks? What variable in this entire equation? What am I looking for? D. I've got Vi. I've got mass. I have to now think about this. Think about this for a second. What is providing the work that's slowing you down? Friction. So this F right here is friction. So it's really mu Fn. Again, write yourself a note. This is really friction because that's doing the work to you. You always have to ask yourself with this theorem, what is doing the work? If a pole was doing the work, then it's Fp. But friction is what is causing your kinetic energy to decrease. Right? I'm running, and I'm excited, and I gotta move. I got a lot of kinetic energy. And then I come to a stop eventually, I've got no kinetic energy. Where did the kinetic energy go? It went to friction. It can't go, it can't just disappear. So I've got that times d times cosine theta equals negative 1/2 mvi squared. Stop, guys, listen. We're almost there. Focus a little more. Last problem. Now, I've got mu in this problem, but I don't have Fn again. What is Fn? Think back to the last problem from section 5.1. It's just Fg right now. You can make that assumption when anything is ever moving only horizontally. Fn and Fg are always out of balance. If there's nothing pulling me up, if I'm not jumping up, if I'm not being pulled at an angle, then Fn is always going to be Fg. But I don't have Fg in this problem. I don't have Fg. What is Fg defined as? Everybody. Mg. So what does it turn out? What do you notice? What is not really necessary to know about this problem? Not the angle. We're gonna look at the angle in a second, actually. There's something else. What's on both sides of the equation, guys? And isn't everything multiplied? So isn't that a greatest common factor on both sides? What can you do to that? Cross them off. Again, the mass is on both sides. If I were to solve for mu, I could see they cancel, but I'm just going to cancel them right here. Now I get mu, g, d. What is theta for the force of friction? Be careful. We did this in the last problem. What is it? Yeah, well, the answer would be -1, but what's the angle? 180. Remember, I'm moving this way, sliding on my nice new socks, friction is pushing this way. That angle is 180 degrees. So we do the cosine of 180, which really just means this is -1 right here. So I'm just going to put a negative sign out in front. All right? So notice what I did there. I simply replaced cosine of theta with a -1. So it's -1 times mu gd. So I write it as negative mu gd equals -1/2 vi squared. Okay, -1/2 vi squared. What am I solving for again? So the negatives cancel on both sides, and we'll divide by mu g. Oops, I cancel the negatives. The negatives cancel on both sides, making this 1/2 vi squared over mu g. Okay? If you want to write it this way, you can. Just to make it look nicer. You can put the 2 in the bottom instead of leaving the 1/2 in the top. It's the same thing. Right? You can solve it right now. At this point, you can solve. Or instead of writing 1/2, you can just put divide by 2. Doesn't really make a difference. But notice that the answer is independent of mass. Another amazing thing to think about. Because realistically, using common sense, wouldn't you think your mass would affect it?
Yes.
So this says the following. This says that if you, or your little brother or little sister or somebody much smaller than you, runs with the same velocity on the same floor, on the same planet, because g, right, obviously, then you will go the exact same distance. It's pretty amazing to think about. Mass has no real effect on this problem.
So do we have to do this every time we solve a problem like that, or is it more like a generic solution kind of thing?
It's one of those where you start with W equals delta KE and then figure out from there you gotta go. It's never gonna be the exact same thing as this, no. This is one of those where the formula you need to know is W equals delta KE. And then from there you start just going through the problem. What do you get as an answer? I know the units are meters, but what is the answer itself? What's the magnitude here? Look at you. Did you check your work? Check your calculator. See what you could have done. Come on, folks. Somebody's got to be able to get this. Type it in. If you're making a calculator error, please be careful. Square the velocity first. You need parentheses here. Look up, look up.
Oh, that's why.
You need parentheses here. You should get 0.458 or 0.46. You need to square this, then divide by this inside of parentheses, please. The denominator needs parentheses. So tonight, remember what you're doing. Hey, just 5-1 homework. We'll pick up with 5-2 tomorrow. Tomorrow's a C day. Okay, keep that in mind. Focus. So, potential energy. Okay, we talked about this, we alluded to this. You speak one on the time. There we go. We alluded to what potential energy was at the beginning of our lecture yesterday. And the idea of potential energy is that something has the possibility of changing, of moving, of releasing energy, of changing that energy to a different form. So the word potential is really what's at hand here. And the first type of potential energy we look at is called gravitational potential energy. Okay, gravitational. And gravitational potential energy is a function of the height of the object. Okay? It's due to the height. That's all it's due to. The height of it because of the gravitational field that you're in. So if you're a certain height above ground and you fall off that location to land somewhere lower, you're going to end up changing energy into kinetic energy as you're falling toward the ground because you pick up velocity. So you have the potential to change into a different type of energy based on your location. Okay? And that's why in the beginning definition here we talk about potential energy as being the energy of position, shape, or condition of an object. So the shape of an object. For example, if I were to take a spring and compress it, I've changed the shape, haven't I? What I'm doing is I'm storing energy in the spring. As soon as I release it, the spring shoots out and pushes off. And it takes that energy and converts it into motion, whatever object is on there. That's how something like a catapult will work. A catapult usually is torsional spring energy, and then you release the lever and it launches forward. It's stored energy based on its shape. Okay? Based on its shape. The condition of an object could have to do with some things like, is an object a solid, a liquid, a gas? Does the actual chemical makeup of it change, or its actual condition? So in this diagram right here, we have heights of A, B, and C. So if the ball was at height A, in this diagram would have the highest possible potential energy it could have, assuming that was the highest. At B, it would have about half of the energy that it has at A, because the height is about half. I'm estimating, obviously. And then at C, the potential energy you consider to be 0, if you're calling C ground level. Again, remember I talked yesterday, it's all relative, I said, I used that word. It's all relative. Right now, my potential energy is 0. But if I were to, consider myself compared to the ground outside, I'm 4 stories up. So if I'm standing on a ledge or a windowsill or something like that, which I wouldn't be doing, obviously, I would have a lot of potential energy right there. But right now, I consider the fact that this floor is like the ground, okay? Ever fall downstairs before? I've done it. I mean, if you just trip, right, when you're walking, you start stumbling and you lose control of yourself. Well, it's because you're at a higher energy state and your body wants to naturally go to a lower energy state. So you keep falling down because of gravity, really. It's pulling you down. So, again, this is a function of gravity, which on the Earth is constant, assuming we're at the same height or generally the same height, the height of the object itself, and the mass. So look at the formula. It's m times g times y. And again, we can prove that this is joules. How do I prove that this is joules? I take a look at the formula. Okay, I take a look at the formula. I write on my units. Mass is in kilograms. Gravity is in meters per second squared. And height is in meters. And if you think back to yesterday when I derived this with work, and I looked at the work formula to compare it, we ended up getting kilogram meters squared per second squared. And that was what a joule was. And we get it again. So the units here are indeed joules.
So you can never have potential energy in the x direction, right? Or
Potential energy is only in the y direction. Yeah, that's a good point to make, okay? It's only based on the height because gravity works in the y direction.
so if you're like pulling something, what if you like pull
You can have spring potential energy horizontally and other stuff like that, but you're never going to have potential energy located or based on a location for x direction. Okay? A very simple example to start here. We see that a 40 kilogram object is raised from the bottom of a well using a pulley system. Okay, using a pulley system. The depth of the well is 25 meters and the object is raised 3 meters above the rim of the well. Determine the change in potential energy of the object. So this is the kind of problem that I specifically asked because I want you to understand about relative changes. So where is this object to start? Where is it located? What does it say? At the bottom of the well, right? At the very bottom. And the actual well itself is 25 meters deep, but you raise it 3 meters above the rim of the well. So here's the object down here at the bottom of the well. Here's the well drawn. And then it gets raised all the way up to here. So it goes 25 meters, and then it goes an additional 3 meters. So you need to start thinking about these problems in the fact that, or in a way such that it will make it easier on you. So what would it make it easier to think of the ground level in this problem? What should I call ground level? Ground level is a relative term, don't forget. It's a reference line. Because technically speaking, right, here's the lip of the well. Here's the lip of the well. This is probably the ground right here, right, outside of the well. And this is you standing out here, raising the object up. So technically speaking, we call that ground level. But what should I call ground level to make the problem easier on me, Kira? The bottom of the well, or wherever the object is to start, which is, in this case, the bottom of the well. That's what we'll call the zero line, or ground level. So go ahead and call that zero or ground level. That's what this is here, just signifying 0 meters of height at that location. So as a result, it makes the problem easier. You don't have to worry about thinking it in several parts and negative dimensions and negative height. You follow what I'm saying here? If an object moves up, it gains potential energy. If an object moves down, it loses potential energy. That's conceptual. Now we apply that to mathematical. So call this 0 to make it easier on me. So what's my change in height in this problem in the end? How many meters overall?
28.
28. It's 28 meters. It starts here, it goes up 25, it goes another 3. So I know it's 28 meters is my change in height. Okay? 28 meters is the change in height. You can call it delta y if you like, that's fine. The formula just uses y though. The mass of the object is 40 kilograms. And I'm on Earth. So gravity is 9.81 meters per second squared. Notice again, I'm not using negative 9.81 here because I'm looking at energy and I'm looking at the change in energy as a function of the height. Okay, I'm not looking at the negative 9.81. It's not an acceleration that's downward. Okay, so I go ahead and look at this problem and I say potential energy equals mgy. And just plug in. I called this earlier in the year a plug and chug. You're plugging in and just chugging through the problem, okay? More of a simple kind of problem to get you a little preview of potential energy. What do you get as an answer? How many joules? And it's going to be a big number. Remember, we talked about this yesterday. You're going to get a large amount of joules in these problems because joule is a very small amount of energy, actually. You got 40 times 9.81 times 28.
10,987.2 joules.
All right, 10,987.2 joules. All right, so I might call that 987 kilojoules. It doesn't matter really, but I want you to make sure that you understand that obviously your units can change, just so we've done them in the past. Any questions on this one? Very simple kind of problem, right? Let's look at one that's a little more complicated now than just simply multiplying 3 numbers. So we have an ant, and an ant's potential energy keeps changing since it's constantly walking up and down these little ant hills. And it's carrying heavy pieces of food that vary its overall mass. So maybe the ant's walking by, picks up a piece of bread that somebody left behind. So now the mass of the ant changes. So we're going to see that the mass is changing and the height is also changing. So we say the following. At instant A, and I want you to visualize, please, visualize as you hear this. At instant A, it's carrying 3.5 times its mass, which is what ants can do. We can never do that. Imagine carrying 450 pounds and walking on your back. Okay, it's very heavy. Ants' body strength, they can carry up to like 6 times their mass. So they're carrying 3.5 times their mass in addition to their actual mass, obviously. And it is at half the height than it is at instant B, where it's not carrying food at instant B. So now it's only its own mass. At which instant does the ant have more potential energy, and by what factor? So draw yourself a little diagram. Okay, here's the ant to start. Here's the ant with food on its back. The mass overall is going to be 4.5 m. How do I know that? Because it's got its own mass, which is m, plus 3.5 of its mass, which is 3.5 m, plus m gives you 4.5 m. M is just some variable, some dummy variable. Okay, I'm calling m, if we say, let m equal the mass of the ant. Okay, the mass of the ant. So in the beginning, its mass is its own mass m plus 3.5 m's, giving you 4.5 m's. Now, it goes like this, and it goes up to another anthill. And at this anthill, it dropped the food along the way, and now the ant is by itself. So what's the mass at this point in time? Just m, just the mass of the ant, because it's by itself. It's unknown, clearly it's unknown, but it doesn't matter that it's unknown here, because we're looking at relative differences. Now, height. What does it say about the height? It says that when it's carrying at point A, let's label this by the way, A and B. At point A, it is half the height that of point B. So, what should I call point B's height? 2y. So I could say that y2 is really double the height of y1, and y1 is just 1y. So no variable, no numbers noticed, all variables here. So this is a height of y above the ground. If we call this ground level, it doesn't really matter what ground level is here. Okay, because we know it's just double. That's y. And this is twice the height, because it told us that at A, it's at half the height. If you had done this, which is correct as well, you could have called this 1/2 y, and called this y on the right. Again, if you call this 1/2 a y, this just becomes a full y. As long as these are double each other, that's all that matters. And now at this point in time, we can go ahead and figure out our potential energies in all variables. So at instant A, remember, potential energy equals mgy. So it's the mass, which is 4.5 m, times g, times y. At instant B, what's the mass now at instant B? Just m. It's just the ant by itself at instant B. Gravity is still there, but now what's the height at instant B? Yeah, it's double the height of A, so it's 2y. So in the end, it looks like we get 4.5 mgy, and here we get 2 mgy. So which of these locations gives you more potential energy, A or B? Which of them is a higher number? Just look at the coefficients. At A, which is not obvious, because we can see that the ant moved up, yet he lost potential energy because he lost his mass. Remember, potential energy is not only a function of height, it's also a function of the mass of the object. So although the height doubled, the mass went down by a factor of 4.5 there, right? So that was the first part of this problem. It said, which one of these has a larger potential energy? Then the second part said, by what factor? How do you find a factor of increase between two numbers? What do you do with those two numbers? It's not subtract. Be careful. So I wanted to go over that, because if you subtract them, you're getting a differential. It's not a factor. It's just a difference between them. A factor. How do you get a factor of increase? If today I ate 3 bagels, or that'd be terrible, geez. And then tomorrow I ate 6 bagels, what would that factor be of increase there? So what did you do? Well, you figure out what to multiply by, or just divide. So if you want to know by what factor does 2 increase to get to 4.5, just divide the 2. If you want to find the factor of increase, and this is for all things in physics, you should definitely know this, because we're going to see more problems like this where you want to find a factor of increase. Take the first quantity that's larger, over the second quantity, what cancels? Good. It's in both terms, right? So you just get 4.5 over 2, which is 2 point, yeah. Okay, $4.50 divided by 2 is $2.25. Whenever I have quarters and halves, I always use money. It's very simple thinking ahead. So the factor of increase is 2.25. Right, 2.25. That's how much the potential energy of this ant has gone up by. Anybody think of as X in the past? What do we call it? Displacement, right? We call X displacement. And this is a type of displacement here. But we want to be specific. In this instance, when we're looking at elastic potential energy, okay, for something that's stretched or compressed, X is the change, should write this down, X is the change in length. So technically speaking, some books will use delta X because of the word change, obviously. All right, but X is really the change in the length. And what do I mean by length? We'll take an example of a rubber band. So let's say a rubber band has a length, if you're holding it between your thumbs like this, right? So one loop is here, one loop is here. Let's say the length of the rubber band is like 5 centimeters. And then suddenly you pull it back until it's like 15 centimeters. The change would be how many centimeters? 10 centimeters. So again, it's how much you change it by. So traditionally, we sometimes say that the X in this formula is really the X free, meaning the normal length, minus the X, and you could say stretched or compressed, but just call it X0 or X whatever. Something else that's stretched or compressed. So if the free length is usually like 5, and then the stretch length is 15, you get a difference of 5 minus 15, you get negative 10. Now, notice you're squaring X in the formula, so it really doesn't matter for this instance if X is positive or negative because you're squaring it anyway. All right? But when we get to, oh bless you, when we get to Hooke's law, we're going to see that whether X is positive or negative does affect the problem. Okay? But for the sake of this, we're looking at the free length of it. So let's say again the length of the rubber band was 5 centimeters to start, and then you stretch it to be 15 centimeters, the X value would be 10 centimeters. Okay, just as a simple example to start with, X. Now, this other thing in the formula, K. K is a material property. A material property, such as density. It's not density, but similar to that. Or mu. Mu is a material property of the two surfaces in contact. K is a material property. It has to do with the strength of the spring or rubber band or whatever is being pulled or stretched. Okay, so traditionally in physics, when we look at problems like this, we look at a spring. So imagine you're in a spring and you're able to, like on your pen, you click your pen. Oh, you're off silence now. But on like a pencil or a pen, when you click it, there's a little spring in there, right? And when you click it and it makes the pen show up or the pen stick out of the end of it, the spring is compressed. And you can feel that because the top of it is just wobbling now. And then when you click and let go, you can actually see the end of the pen shoot back up because the spring is, using that energy that's stored when it's compressed to then expand. So for these problems, when we're looking at elastic potential energy, we model things as springs. So we call K the spring constant. K is known as the spring constant. And again, I'm using the word spring, but it could be anything. It could be a rubber band. Anything that could stretch, literally, has a K value. And everything really can stretch, by the way. Some things have very low what are called modulus of elasticity, which means it would break easily. So for example, if you take something like a rubber band and stretch it, it's easier to stretch, right? Take a plastic bag from the grocery store. You can stretch it, but what happens to that? Does it go back to its shape?
No.
It permanently deforms. It reaches what's called its yield strength, and it starts to deform, and it starts to narrow in the middle. And you get that little like bowing effect, like a bow tie where the middle of it's slender and the out part is bigger still. Eventually the plastic bag would just tear, right? So although a plastic bag has a K value, it's not very compressible or stretchable, or I guess flexible would be a good word for that. So K is the spring constant. Can anybody, this is really difficult to figure out, can anybody figure out what the units of K are? And if you know it already, because you may have seen this, just hold off, but can you figure out what K's units are? Anybody know how you would figure it out? We've done this before, where we've tried to figure out units. What do I usually do with the equation? Try and recall from ones we've done in the past. If I'm trying to find out the units of K, shouldn't I list all the other units I know? What are the units of potential energy? Ooh. What are the units of energy? What is it? Joules. Good. Okay. What are the units? Again, we don't know what K's units are. We'll leave it blank. What are the units of displacement, or X? Meters. Or in this case, it was centimeters, but usually it was meters. Yeah. And that is squared, right? The 1/2 has no unit, so I can get rid of that. I don't need the 1/2. So the question becomes, what has to go there so that the units are balanced? But the real question becomes, what is the definition of a joule, really, if we want to actually figure this out? Okay, if we want to figure this out, we have to figure out what the definition of a joule actually is. So think back to potential energy. mgy, that's the units of a joule, right? When you multiply m times g times y, you get joules as your units. So m, its units is what? M as in mass. What are the units of mass? kgs. So this is mass. I'm using gravitational potential energy to remind myself of what should be here. So mass times gravity. Gravity's accelerations, it's meters per second squared, not meters squared. Meters per second squared. And then my height is in meters. So that's what a joule really is. Well, I still don't know what goes over here. So let's see what's still missing. Okay, let's see what's still missing. So we have kilogram meters squared per second squared equals something times meters squared. So I've kind of broken everything down into what it looks like. So what's missing that should go in this box right here that's on this side, that's not showing up on the right-hand side? Kilograms over second squared needs to go there. And that's absolutely right, but we can write that differently. There's a way to write that differently. Okay, and let me show you what we're going to use. We're going to use a Newton per meter instead of a kilogram per second squared, although those are the exact same thing. Okay, and it's tough to see that. Okay, these are the units of K. We're going to use newtons per meter, but let's prove that that's the same. So if I had a Newton per meter, a Newton, if I remember, is mass times acceleration. That's where newtons come from. Bless you. So it's kg m over s squared. Now this m here we can't forget about. That's got to be down here. So as a result, a Newton over meter, the meters cancel, right? Like that. And we end up with this unit right here. Kg over s squared. Well, that's what we had up there. So in reality, a Newton per meter is the exact same thing. God bless you. Now, we don't use kilogram per second squared for a specific reason. Think about a spring. Think about a spring. If you're trying to think about the strength of a spring that's stronger takes what to stretch it? More, a lot, a little? How do you think about it?
More force.
More force. More force. So look at the units. The units we're going to use for K is newtons per meter. And this is physically what it means. If the K value of a spring is 5, right, 5 newtons per meter, it means it takes 5 newtons of force to stretch it 1 meter. It's a rating. Okay, it has to do with the material properties of the actual spring. So if something has 10 newtons per meter, it means the higher K value is a stronger spring. It takes 10 newtons to stretch it a full meter. All right? Now, a full meter of a stretch isn't really reasonable, right? Think about that. How big would the spring have to be? A meter is like this long. So to stretch something this far means the spring itself must have to be very large, right? So a lot of the time when you see K values, they're usually in like newtons per centimeter or newtons per millimeter, okay? Or if they're in newtons per meter, then it's usually a value that you might want to consider, not converting, but consider thinking about what it physically means. Because 5 newtons per meter, it'd be like taking, it's almost impossible taking a cord and stretching it a full meter. Nothing's going to stretch an entire meter unless you have a really long spring to begin with. Okay, maybe a slinky would be something like that. Okay, a slinky could easily stretch a full meter. A slinky would have a very low or high K value. Have you used slinkies before? They go down the stairs, right? You've seen them? Would that be a low or a high K value? Why?
Instead of big off
Yeah, isn't it pretty easy to stretch a slinky? If I hold one end and Mike, you hold the other, and I just keep walking away, doesn't it stretch very simply? It sags, right? A slinky. It's not very strong. It's got a very low K value, as opposed to like if you look on your car, the shocks that are on your car. When your car hits a bump, it doesn't sit there and do this forever, right? It would have very bad hydraulics if that happened. So you put what are called dampers and springs, and the spring that's on a car has a very high K value. What about the spring in your pencil or your pen? In your pen. High? Why would you say high? I thought you had your hand up. That's why I didn't.
I didn't, but I'll do it. But because it takes more force to bring.
We'd have to check, I guess, right? It wasn't meant to be like a trick question, but it kind of is a trick question because it's really small, the spring in your pen, but its K value could be very large depending on how much it's stretching. So if you take it out and you pull on it, is it difficult to pull on a spring that's in your pen? So it might be very low, but it might be very high. It really depends on the pen individually or the object individually. But for specific things, like something like a car, you know it's got to have a high K value because that spring needs to be able to withstand a lot of force. Whereas a pen, it's only your finger pushing down. But it could still have a rather high rating depending on the size of it itself. Okay, so it all depends on what you're looking at. So when we do a lab for this, we're going to take a look at a lab that involves deciphering or determining what the K values are by applying forces, determining how far the spring stretches, looking at its period of oscillation. Okay, so we're going to really do that to see what the physical properties are for K values. But what you want to remember is that as K goes up, the spring gets stronger. Okay, there's other words that are used. So spring constant, spring stiffness, spring rigidity, how rigid the spring is, those are words that are interchangeable that your book might use. So if in a problem it says the spring rigidity or the spring stiffness or the spring constant is the following, that's talking about the K value. All right, the K value. Let's take a look at it. Oh, this is what I was talking about. Do you want to get an idea? So imagine this is the object. All right, this is the full length of the spring normally. So it's normally like this with a mass at the end of it, and it's attached to a wall right here. And then a force is applied on the object, and what happens is the spring compresses to be this long. So from the front of the object to the front of the new object, or where it would be, is your X value. Okay? That's X right there in red. Remember I said X is the distance in which you compress it, okay, or the change in length of the spring. So the change in length of the spring there would be from the beginning of the object after it's been all the way compressed to the beginning of the object when it was at its free length. So this is free and this is compressed length. You could also stretch a spring. So you could either compress it or you can stretch it, either way. Quick, I edited them in my notes, but I didn't edit them on this one, and they're probably in yours as well. So let's say that the free length, to be more reasonable, I use numbers to make them easier, but then I realized a spring is never going to be 2 meters long. It's kind of ridiculous. So let's think about a spring that's like only like maybe this big, so like 10 centimeters. And let's say that it's compressed. It says the spring is compressed from its free length of 10 centimeters to a length of, I don't know, 3 centimeters. Let's say it's compressed all the way in. If the rigidity of the spring is represented by a stiffness of, and let's use a larger number here. Let's use 500 newtons per meter. Okay, is represented by a stiffness of 50 newtons per meter, then how much potential energy is stored in the spring? So the whole idea of springs is that you're storing energy, like a catapult. Even, well, trebuchet is different, it uses counterweights, but it's still storing energy. But here we're going to look at and see how much energy is actually stored in the spring. And in a situation like this, if there's an object on the end of the spring, like a pinball machine, you pull back on the lever on the pinball machine, right? The spring compresses, you let go, and with a certain velocity, the plunger shoots forward and hits the pinball. And it gives it some initial velocity. That's a perfect example of conservation of energy. You're taking the energy that's stored in the spring, and it's turning into kinetic energy once it hits the pinball. And the pinball starts moving, and it has now kinetic energy. So you're changing energy. And we're going to see that in this next section that we're going to look at today. So if we want to determine how much spring energy exists, let's take a look at this problem and think. So what do I know? What are some given information here? Some given. Yeah, 7
centimeters.
centimeters. Okay, remember x is the change in length. The change in length. What else do I know? Something else. Paul? What is K? Good. And besides the fact that the problem says it has a spring stiffness, which is really what K is, you could also look at the units. You can see newtons per meter. Okay, you can look at the units. Now, can I go ahead and solve this problem right away? Why not? What do I have to do, Mike? I heard you say no. Okay. By the tone of my voice? Yeah. I have a tendency to, prompt you with that voice. Why don't you think you can start this one right away? What do you have to do still? Yeah, we need consistent units. So although the given dimensions were in centimeters, let's convert them to meters. What's 7 centimeters? Centi is hundredth, right? Hundredth? Point what? Not 0, 0. Yeah, just 0. Remember, the word centi means hundredth. So 7 hundredths is that right there. That's what 7 hundredths is. If you add another 0, it would be 7 thousandths. And that would be if you were converting from millimeter. So we got 0.07 as our compression length. We got 500 as our K value. Now it's a plug and chug. Okay, just go into the problem, plug it in. PE equals, and sometimes you can write like PEE or PES, S for spring or E for elastic. Okay, just to specify that it's not regular potential energy. So half of 500 is 250, and then take 250 and multiply it by 0.07 squared. This will give us the amount of energy that's stored. Remember, this is a very small spring, so we're going to not get a very, very large number like we've been getting for joules in the past. Anybody got it? What do you got, Marianne? 1.22? 23? Do others agree?
Yeah.
All right. So yeah, it's only a joule of energy. Again, think about this for a second, folks. You're taking a spring that's only like this long, and you're compressing it to here. It's not a lot of energy that you're storing in that spring. Okay, if you have a spring that's more heavy duty, with a higher K value, with a longer compression rate, so if it was more than 0.07, okay, you'd have a higher value. Remember that everything is directly related here. If K goes up, PE goes up. If X goes up, PE goes up. They're all directly related in this problem. Okay? Before we go into the next section, I want to start 5.3 today so we get a little, head start on this. I want to quickly just talk about the, remember the extra credit you guys did for the sliding? Just to give you some results. So 15 groups did it, or 15 data points were taken. And some data points, some people only slid like 0.8 meters. Others slid 3.2 meters. So there was definitely a high standard deviation, and it really depended on how fast you were running and the surface you're running on. And if you remember from the other day, my generic solution for D was VI squared over 2 mu kg. That was the solution for distance traveled. And think about it for a quick second. Velocity is directly related. And think about it. If you're running faster and you start sliding, aren't you going to go further? A good example, Pat, yours, you went the furthest. You and somebody else actually tied the exact same length. But both of you in your videos, if you look, were running full speed and they came to like a jumping stop and just glided across the floor. So there, what was it, 3.2 meters, something like that? Yeah, that was one of the highest ones. And it was because his velocity was a very large number. And you see the direct relationship here between velocity and distance? It's in the numerator. Now, think about mu. Mu is in the denominator, which means it's what related? Not directly, indirectly. See the problem thing again? Okay, indirectly related is mu. So if mu goes up, D goes down. And think about that for a second. When mu goes up, isn't there more friction? So wouldn't you slide not as far or less distance? So it makes sense logically that when mu goes up, the distance traveled goes down. The overall average was 1.8 meters. And so the other class was kind of a period behind you guys, so I worked with them on that problem yesterday. So we parameterized it, which that's not even a word really, parameterize. But we changed the parameters V and mu in the problem to fiddle around with them to come up with 1.87 or around there. So in the problem I gave you in class, if I recall, V was 1.5 and mu was 0.25. And it turned out that if you ran a little faster, and this gave us a distance, by the way, in class of 0.5 meters, around there. But the average for our class was 1.87 meters. So either one of two things. Either you were running faster at home than we ran in the problem, or mu was lower at home than it is. So what we tried was we tried changing mu and v in this problem independently and seeing what the effect was. And we found that if a mu value was like 0.15 and a v was given as 2, which are both absolutely reasonable still, they're both close to what we had, 2 meters per second would literally, like this is 1 meter per second. So 2 meters per second is not that fast of a running start. So if you used about 2 meters per second and 0.15 is mu, you get around 2.0 or around 2 meters as the distance traveled. So that would be the equivalent of the average that we got from everybody's data. But some people ran faster. Some had floors that were tiled. Some slipped on the floors as they ran because they were so slick and the mu was so low. No idea who would do that. And then at the same time, we also have to consider that there's also a lot of experimental error. Some of you really didn't measure the right way. That was the other thing. Like, I was watching the measurements of the video, and sometimes I was like, oh, geez, I got to teach them how to measure sometimes. So we have to go over some of this kind of stuff. So for example, if you start sliding here, and you end over here, but I noticed some of you did it on like a wooden floor, so you measured parallel to the wood panels, but you slid at a diagonal. So like, instead of measuring, say it was from Kira to me, right? And this was the distance slid. People were measuring from Kira to where like Victoria's sitting because the wood panels went along the floor that way, so it was easy to put your ruler up against it. But in reality, you have to measure from A to B. Then some other issues were like people didn't have tape measures, so they were using a ruler, which is fine, but there's definitely going to be some error, when you stack a ruler over and over again. But that's for experimental error. So again, reasons as to why you're getting varying answers: change in velocity, change in mu based on the floor you used, and then obviously just the way it was measured itself. Okay? I think Kev, you guys did on a gym floor, right? Yeah, and you had one of the lowest values. That makes sense. Think about it. When you play basketball, don't you hear like all the squeaking from the shoes? Aren't those gym floors meant to be very high friction actually? Although they're smooth and slick, they're actually a good amount of friction on them. And when you guys were doing it, I noticed you only went like around a meter, right, for both of yours? Because you had that high friction value. Okay, so depending on the situation, the variables changed or the parameters changed. I'm telling you, except for the springs, obviously, but you can definitely finish this one now. Okay, so I expect you to finish this tonight. All right, finish this up. We're going to start 5.3 now, but you're not going to have to do 5.3 homework. But finish this homework from 5.2 up tonight. 5.3 is a continuation of 5.2. All right, so everything we've learned right now will help.